Welcome back. In order to optimize the performance of our solar panels, we need to point them in the direction that maximizes the incident irradiation over the entire year. In the previous video, we discussed the three different components of light: direct in red, diffuse in green, and albedo in orange. We derived expressions for these components as a function of the tilt of and azimuth angle of the PV module. So now the goal is to find out for which module tilt and azimuth the annual irradiation on the module is maximized. We will therefore focus on two optimization concepts: a fixed panel and a panel with a mechanical tracking. So the learning objective of this video lecture are to understand how the annual solar energy incident on a PV module can be optimized for using optimal tilt and azimuth for a fixed PV module and using mechanical tracking like vertical, horizontal and dual axis tracking. The most common way to find the best combination of tilt and azimuth is to simulate the performance of the PV module over an entire year. However, this is out of the scope of this MOOC. Therefore, I will introduce you quickly to some general guidelines. A rule of thumb for a quick optimization is to use an angle equal to the latitude of the location facing south in the northern hemisphere or north in the southern hemisphere. The highest yields are obtained using mechanical tracking, of course. Let's see how a sun tracking and fixed PV panel is working in different places around the Earth. We will first go to London. London has a latitude of around 51 degrees. Consequently, the range of tilt angles throughout the year for a panel tracking the sun varies from 28 degrees to 78 degrees. The panel in this case is oriented towards the south. For a fixed PV module, the optimized angle of tilt will be 35 to 40 degrees facing south. Moving closer to the equator, we have Cairo at around 30 degrees latitude. We notice that the range of tilt angles has diminished to around 6 to 54 degrees. The optimized angle of tilt for fixed PV panel in such a case would be around 20 to 25 degrees facing south. Now let's go to the southern hemisphere where the solar panel mounted in Sydney. Sydney has a latitude of around 34 degrees south. Note that being in the southern hemisphere, the panel is oriented towards the north. We see that the range of tilts experienced by the PV panel is from 10 to 58 degrees. The optimized angle of tilt of a fixed PV panel in such a case would be around 30 degrees facing north. It has been seen in practice that the optimized angles can give up to 70 to 80% of the maximum PV yield. As long as the solar panels are facing in the right direction in general, that is facing south for a panel in the northern hemisphere and north for a panel in the southern hemisphere, it is usually observed that the variation in the optimal orientation angle doesn't vary the PV yield too much. Consequently, the optimal tilt of the panels help in serving more energy than the optimal orientation. It is also interesting to note that the optimized tilt could also be based on the seasons. That is, we could either use an angle that maximizes the PV yield in summer or in winter. In the animation, we have looked at the position of the sun at noon. Another way to visualize the seasonal variation of the trajectory of the sun is by means of an analemma. Here the analemma of the maximum tilt of the sun in the sky in Delft in the Netherlands is shown. The analemma is a diagram that indicates the position of the sun when observed at the same mean solar time every day, in this case noon. Indeed, due to the Earth's actual tilt and orbital eccentricity, the sun will not be in the same position in the sky at the same time every day. In the analemma of the sun, you may notice astronomical important days of the year, such as the solstices and the equinoxes. As shown in the picture on the right, it is possible to photograph the analemma by keeping a camera at a fixed location and orientation and taking multiple exposures throughout the year, always at the same clock time. Let's first focus on the fixed panel. We can calculate a contour plot like the one shown here. On the horizontal axis we have the azimuth of the module, while on the vertical axis the tilt angle of the module is plotted. We can populate the contour plot with the total amount of energy incident on the module in 1 year as combination of tilt and azimuth. This plot is calculated using the tools discussed in the previous video. Firstly, you have to calculate the solar position for every hour of the year. Then we set a range of possible configurations, selecting a tilt angle ranging from 0 to 90 degrees and the azimuth of the module ranging from east to west. For each configuration, we compute the incident irradiance of the module and then integrate this result over time to obtain the energy falling on the panels over an entire year. The point where the incident energy is maximal corresponds to the best possible mounting configuration for the PV panels for that specific location. In this example, the optimal module tilt is around 25 degrees and facing south. Note that in some installations the array tilt angle or azimuth angle is decided for you. This can be the case for a sloped roof mounted system. Moreover, if your energy demand is highest in winter, then you can optimize the tilt and azimuth for the winter months. This will, however, inevitably lead to a suboptimal annual yield. One possibility is to use a fixed panel, where you can choose the tilt and angle and maybe adjust it a few times during the year. Alternatively, a mechanical tracking panel configuration could be used as well that follows the sun during the day. Let's start with this single axis tracker. As the name implies, this tracker only has one rotational axis, so 1 degree of freedom, indicated here by the red line. The tracking system consists of an electric motor controlled by a computer system that changes the tilt of the panel. The computer uses an algorithm that requires the coordinates of the location and the day and the time to compute the position of the sun. This sort of system is called a daily or vertical tracking system because the axis of rotation is aligned vertically with respect to the ground. The electric motor can therefore tilt the panels during the day such that they track the sun as it moves from east to west. Another option is when the axis of the rotation is horizontal with respect to the ground. When the axis is horizontal, the azimuth is kept constant and the module tilt and angle is varied during the year rather than during the day. These systems are called horizontal tracking systems, and they adjust their position according to the altitude of the sun during the year. So during the winter solstices in the northern hemisphere, the panels will have the largest tilt angle. The tilt angle will gradually decrease until the summer solstices. Unlike the vertical tracking system, the electric load is much lower because the rotation cycle lasts an entire year. Note that in both cases it is very important to consider the shading in order to avoid unnecessary energy losses. Finally, we have the dual axis approach with 2 degrees of freedom. The first rotational axis is parallel to the ground and changes only the tilt angle. The second axis is perpendicular to the ground and the other axis, which allows for a change in the azimuth of the panel. The dual axis approach is often used for PV modules with solar concentrators that requires the direct component of the sunlight. The dual axis approach always makes sure that the direction normal to the panel is aimed the direct component of the sunlight, as you can see in this animation. It's very similar to what we have seen with the PIR heliometer for measuring the direct normal irradiance. Here we have an example of a photovoltaic concentrator system that follows the sun during its daily movement in the sky. You can always see that contrary to the conventional photovoltaic system, it uses so-called Fresnel lenses that concentrate the sunlight to intensities of over 1,000 suns. The sunlight is concentrated onto small, expensive, highly efficient multi-junction solar cells. These type of solar cells require high-capacity heat sinks to prevent thermal destruction and to manage temperature-related losses in the electrical performance and lifetime of the solar cell. Therefore, a cooling system is generally implemented in concentrator PV systems. Let's compare the performance of a dual axis tracking system with the performance of a PC system with a fixed tilt angle. We'll use the annual total amount of incident energy received by a surface to compare the performance of the system. So on the horizontal axis of this diagram we have the incident energy for a system with a fixed tilt angle that is equal to the latitude of the location. On the vertical axis we have the incident energy for a two-axis tracking system, both expressed in kilowatt-hour per square meters. We consider, for example, the global irradiance incident on the module in Hamburg, represented by the white circle. The annual amount of incident energy is around 400 kilowatt hours per square meters higher for the two-axis tracking system, going from 1100 to 1500 kilowatt hours per square meters. The dual-axis tracking follows the sun to enhance the direct beam irradiance. So if we plot the value of the direct component, which is the triangle in this case, we can see that 1000 out of 1500 kilowatt hours are due to the direct beam irradiance. The same comparison can be made for other cities. As you can see, the energy incident on the module increases as the location gets closer to the equator. Starting from Hamburg and going south towards Seattle, Rome, Hawaii and Albuquerque, there in New Mexico, the energy potential is almost 2.5 times higher compared to Hamburg, and the difference in annual incident energy between a two-axis tracking and a fixed system is about 900 kilowatt hours per square meters. So it is clear that the amount of incident energy is much higher for a dual-axis tracking than for a fixed system. The difference is more pronounced in locations where you have fewer clouds, like in Colorado, New Mexico or Spain. One last thing I want you to notice in this graph is if we do a linear regression of the circles which represent to the global irradiance and one for the triangles which represents the direct beam irradiance in the two-axis tracking systems, both of them increases with two different slopes. The fraction of energy received due to the direct beam increases moving towards the equator. Indeed, it starts with a share of 65% in Hamburg and it reaches 76% in Albuquerque. In summary, in this video, we discussed that the energy incident on a PV module over an entire year for a specific set of tilt and azimuth. The result is this counterplot that graphically depicts the yearly energy incident for all the possible module orientations. With this approach, we introduced the fixed and adjustable concept for energy optimization. In addition, we discussed mechanical tracking approaches like the single-axis tracking system. Depending on the orientation of the single rotational axis, the tracking system can be vertical for daily adjustments of the tilt angle or horizontal, which adjusts the tilt angle gradually during the year. The alternative is a two-axis tracking, which is employed in photovoltaic concentrators. By now, you understand that a fixed panel has an optimal tilt and azimuth to achieve the highest annual yields. Other factors that might determine the placement of a PV module exist as well. In the next video, we'll discuss some of these other aspects, like module spacing, mutual shading, and functional area use. So, see you in the next video.